Whenever you're ready.
Okay. For this session's last we have Ryan Dougherty to present a paper on covering arrays and perfect hash families of high index.
Okay, so this is joint work with my advisor, Charles Colbourn, most of us have probably heard of him, and two folks from SBA Research. So the covering array problem is a mathematical analog of trying to test software. So imagine that we have 10 components, which are the columns in this array, and pick any 3 columns you want. I pick 3 for you. And what we want to have is for any 3 columns to have all 8 of the 3 sets on 0, 1 to appear at least once. So we can see 0, 0, 0 is there, 0, 0, 1 is somewhere, and 0, 1, 0, all 8 possibilities appear at least once. And so you can think of this as I test the system on the first row, I set each of the components to one of what is called the levels, so 0 in the first one, then I test the second row, third row, and so therefore to test the system adequately, where I can have 3 components interacting simultaneously, I need 13 rows. I definitely need at least 8 rows, but this achieves 13 rows. So the problem here is covering array is I give you 4 parameters, n, t, k, and v, where the array is n rows and k columns with on any symbol set, but a V-ary alphabet. And for any t columns that you pick, you see all v to the t tuples at least once. And we say that these tuples are covered when they actually appear. Another way you can think of this is if we tie a t set of columns and a t set of symbols together, so we overlay the column and symbol set together, we call that an interaction. So another way of saying whether something's a covering array or not is whether every interaction appears at least once. But one of the things that we've seen is if you have a system that is not deterministic, it makes random function calls or has multi-threading, it's not a deterministic process, we may want to have redundancy in the system. So if I have some test that only appears once, maybe it's not going to give me the right answer of what really actually happens. So to help mitigate against that, let a covering array with parameter lambda be where every interaction appears at least lambda times. So the usual definition is when lambda is 1. So another thing that we want to investigate is this thing called the covering array number, which is the fewest number of rows that I need. So from the last slide with lambda 1, we need 13 rows, and in fact you can do 1 better at best. In terms of asymptotics, you need, for fixed number of symbols and strength, the t is the strength, we need a logarithmic number of rows with respect to the columns. And it's pretty obvious for arbitrary lambda, I can just duplicate the array lambda times, and that'll give me a lambda times log k bound. But in fact, we can do better asymptotically. So if we just make a completely random array, and then just see what happens, then what we can actually achieve is a square root times lambda multiplicative bound, which is already much better. And the only non-trivial thing is applying turnoff bounds here. And so that's where the square root lambda comes from. But could we even do better than this? And the answer is yes. So we can actually get almost optimal in terms of asymptotics, and by using the Lovász local lemma, or the symmetric version of it. So it's almost an identical proof, but you just apply the Lovász local lemma in this case. But note, we have additive factor of lambda plus log lambda. We need at least linear and lambda number of rows in addition, because if you remove any lambda minus 1 of them, then we just achieve a covering array with index 1 instead of lambda. So we need at least lambda rows in general, lambda minus 1 rows, but it's just there's some gap in between. And it'd be interesting to see if we can close the gap. And both of these have constructive algorithms for it. I won't go into that. But of course, to have work this with real systems, we want to actually make the things. So some of the work, so basically I'll show you some of the work that we've done. One method, which is from the folks at SBA Research, is something called the IPO strategy, which is you start with an initial covering array of index whatever, then we try to add a column, and then we try to add as few rows as we need to accompany that new column. And we have been applying this, and it shows competitiveness with the optimal covering arrays, not just the ones that arise from this method from duplicating the array, which is pretty nice. But another method, which is basically what I study mostly, is something called a perfect hash family. So it's like a covering array, but it has a different property. So here is still an n by k array, same as before. But now there are lambda rows of this array which have all different symbols. So for example, if v is equal to 3, like 0, 1, 2 are the values, then if I see 0, 1, 2 in these 3 columns, then I'll say that it's separated in that row. But we require that it's separated at least lambda times. And then we have an analogous number for a perfect hash family. It's the minimal number of rows for this kind of perfect hash family. So if I want to make a covering array out of this, then we have a bound that looks like this, which is, and the proof is pretty simple. You take value I in the PHF, and then you copy and paste column I in the covering array, and verification is routine from that. That you actually get k columns because you just you have k columns before, and you just replace a value with a column, and in fact you get a covering array here of potentially many more columns. But in terms of higher index, the answer is almost exactly the same. But the thing here is we can actually play with the indexes on each of the ingredients. So I can try to pick an optimal covering array of a specific parameter and an optimal PHF of a different parameter as long as their product is at least the index that we are after, which is pretty nice. So, oops, get back here. So in terms of computational cost versus optimality of the size, that's something that needs to be researched further. But there are improvements on this. I won't go into those. So let's study PHFs. So here's an example PHF on 6 rows and 12 columns. Then we see in these 3 columns are only separated once in those 3 columns. But in fact, I wrote a program to check, well, quite a few of these 3 sets are separated more than once. So that gives us good evidence to say that we can actually do better than just copying and pasting. But exactly the same way of covering arrays, we get the nice asymptotic bound. Non-trivially, the optimal size of a PHF with 8 columns, 5 symbols, and strength 3 is 2 rows. And the best thing that you can possibly do is duplicate that array. And it's actually not that hard to show. And there's an infinite class of PHFs that behaves like this. But it's not necessarily true that if you have a PHF with everything separated exactly once, that the best thing you can do is just copy the thing. Sometimes you can actually do better. So something that would be really interesting to settle is when is that actually the case? When is it a necessary and sufficient condition? For a simple direct construction, for a normal PHF with an index 1, then all you're asking is for every pair of columns to be different. So then just list all possible columns, and then that gives you that number of rows. But here you only need one more additional row because all you need to do is take all columns of even weight. So all of those with an even number of ones. And so therefore they separate in 2 places, and then therefore you're done. There's actually, if you have v at least 3 or lambda at least 3, this is actually an open problem in coding theory. And this is a special case of that. But if we want to make these things, what we could do is say, I want to put the best row then the next best row, then the next best row, and stop when I actually have a PHF that I want. But it's NP hard, as you might expect. So we apply conditional expectation. So I generate a row and I compute, does it separate more than the expected number of things that it could separate? But we can make this a deterministic process. So we just look at, in this row of indeterminates, we just pick values and we pick columns one at a time, and then pick a value that maximizes the expectation. And then we just continue through, and the great thing is that it matches that first probabilistic bound, which is pretty nice. So just as computational stuff is concerned, the bottom line is the best known sizes of PHFs of index 1 on my tables. The other black lines are just 2 times and 3 times that value. And then the red lines are the corresponding applications of this conditional expectation method. And it seems that even if we're getting relatively high index, we can still compete with just copying the array. A great thing is that in the best known results right here, not one of them arises from conditional expectation, but the red lines are entirely from conditional expectation. So in fact, there seems to be quite an interesting thing that is going on here. So 2 more slides, I promise. What we have seen is that if you have a relatively small number of columns, the best thing you can do is just duplicate the array. But in terms of asymptotics, once you go into many, many columns, then you only need a very tiny number of rows in addition. So, but in terms of like actually making these things, then most systems use a moderately large, say, a few hundred number of columns. What happens in that case? That would be something to really explore. But I like this question the most, which is, I give you the absolute number of rows. I cannot decrease this or increase this. This is the most number of rows that I'm allowed to test in this system. Then how high can I make the index? How much redundancy can I actually have? And then meta-heuristics or computation, that would be something to explore. Something called the covering perfect hash family, which I haven't covered, which is essentially like a PHF, but it expands out into a covering array. And these have given the best known values on the covering array number. How does it actually work with higher index, which is something really to explore. But and the final thing is, covering arrays help you determine whether a fault exists. Something called a locating array actually tells you where the fault actually is, which interaction is causing the fault. But they are harder to actually construct, but they are actually much more applicable to real systems. Okay, so if you want to look up the best known PHF values, they're on my webpage here. And if you want to look up the best covering array numbers, they're on my advisor's website here. So that's it.
Are there any questions?
I know we all want lunch.
Thank you again.